Hello students, this is the third important physical chemistry topic which you will encounter in your 2 years in college, right? So it's actually on chemical equilibrium. Most of you will have some knowledge of chemical equilibrium in secondary school, okay? I think in secondary school, this particular topic is known as reversible reaction. It's really dependent on how your teacher back then positioned it. Yeah, so the most famous example you are aware of is actually the Haber process. So it's actually the production of ammonia. So you learn it as an equilibrium process where the reaction doesn't go to completion. But most of the time in secondary school, you do not encounter any kind of calculation involving chemical equilibrium. So most of the answers which you need to give when you draft your answers for assessment questions or for discussion, they are usually qualitative based. So the difference for H2 chemistry is that quite a bulk of it is devoted to calculations. And of course, there's another 40% of it which you probably need to know for qualitative responses. Okay, yeah. So without further ado, I will just go straight into it. But maybe I can use this particular topic as a starting point to remind everyone that equilibrium is actually a very important topic in college chemistry. The reason is because this is not the first equilibrium which you're going to learn throughout your 2 years. Yeah, there are other kinds of equilibrium which you will encounter. So maybe I can give a very short summary here. Okay, so right now you are learning chemical equilibrium, which is either Kc or Kp. Okay, we call them equilibrium constant in concentration term and in pressure term. Okay, so you're going to learn this in JC1. When you move on to JC2, right, you're going to learn acid-base equilibrium, where you're going to encounter the acid equilibrium constant, the base equilibrium constant, and the ionic product of water. So you're going to encounter three more equilibrium terms. And then after your promotional exams, okay, sorry, I forgot to mention this. There's actually one more before you go move on to JC2 lah. So after your promotional exam, there will probably be a home-based learning focusing on KSP, so we call solubility products. Okay, so you notice that throughout your many months in JC learning chemistry, right, you will encounter many equilibrium constants. Okay, so I think the most important thing is have a broad overview on what exactly equilibrium is, and be in the know that, or be aware that when you tackle this particular topic, the fundamentals of chemical equilibrium will actually helps you to understand the rest of the topics which you're going to encounter later on. Yeah, especially so for KSP, KA, KB, and KW, which you're going to learn after promos and next year. Yeah, because from experience, many a times your seniors, when they're actually doing this topic, right, they kind of forget what they learned in chemical equilibrium, and they encounter a lot of difficulty tackling these topics. Yeah, so maybe if I were to put it in a very blunt way, if you get your foundation right for chemical equilibrium from day one, it actually helps a lot in your journey later on. Okay, yeah. But not to forget one important thing lah. Chemical equilibrium is intimately related to thermodynamics, because where your position equilibrium lies has a lot got to do with delta G as well. Yeah, so towards the end of this particular topic, we're going to do a link up between delta G and equilibrium constant, and you will have a clearer view of what exactly is happening. And of course, reaction kinetics, you learn it after energetics. Okay, I hope you are not confused by it as well, because remember that for thermodynamics, we are talking about the energy content and whether a reaction can go or cannot go. Okay, so that's based on thermodynamics, or that's based on delta G. In kinetics, we are looking at fast or slow. Okay, fast or slow in the sense we are looking at whether the reaction has a high or low activation barrier, or which is the rate determining step where it has the highest activation barrier. Okay, and then now we're actually back to thermodynamics. Okay, although it's in a broad way. Yeah, we are determining where the position of equilibrium lie towards. Okay, whether the equilibrium can be established fast or slow, okay, is really temperature dependent as well, and its activation barrier dependent. Okay, so in this aspect, we are not really focusing on fast or slow, but we are really looking at where the equilibrium position, okay, is it's being lie towards. Is it more product heavy or is it reactant heavy? Okay, so the value of the equilibrium constant will actually tells us, give us a clue on that. Yep. If you look at the learning objective, of course, there are quite a few here. Not as much, not as many as kinetics, not as many as your uh, um, thermodynamics. Yeah, but these are just the so-called the truncated version. If you actually look at the whole equilibrium, if you include KSP and acid base, then yeah, we'll have a lot more. Yeah, so not to worry. We're just going to introduce you all to chemical equilibrium first. Have a good foundation before you move on to the rest of the equilibrium. Yeah, so I think it helps a lot. Okay, so again, we give you some references here, so it'll be good if you can check out more if you really want to have a slightly deeper understanding. Yeah, if not, then I think going through the lecture notes, the tutorials, and the in-class exercise, and perhaps some of the enrichment activities, they are probably good enough to tackle most of the kind of questions you're going to encounter in H2. Okay, so okay, I'm sure you have seen this before in secondary school. Maybe not the graph, yeah, but I think at this point in time, most of the time when we talk about a chemical reaction, we tend to talk about a reaction in the absolute sense that goes to completion. From our everyday understanding, this seems to be the case because I think in our everyday life, we don't really get to see reversible reaction. Okay, maybe you can just take about half a minute or 1 minute to think through about some of our everyday experience. For example, burning a piece of paper or even cooking. Like you don't see like the piece of paper form from the thin air. Okay, and food they are cooked, you don't see them being raw. So most of the time, our human impression, our daily interaction with nature around us seems to imply that reaction goes to completion. So that is why in secondary school, when reversible reaction was introduced to you all, you will encounter a little bit of difficulty trying to assimilate the information, trying to understand it because it's not natural for us. Yeah, but truth to be told, all reactions are at equilibrium to some extent. It's just that most of the reaction in nature that we encounter goes to completion. Yeah, so that's kind of straightforward, I guess. But yeah, you just need to be aware that most of the time what we encounter in nature, because of our everyday experience and we are kind of like limited in the world we live in, it tends to imply that things goes to completion. Yeah, but that is not the case in the molecular world. Okay, yeah, so something to the effect, if you are going to plot a graph of concentration against time, right? And we start off from the origin. So the product at the start, there's no product, and then of course there's maximum amount of reactants. So over time, you realize that you get the maximum amount of products that you can get, and then the reactant amount will actually go to zero over here. Yeah, so this is our everyday life experience. Yeah, however, there are reactions that are reversible, which of course, given a very short introduction in secondary school, maybe it's about 10% of the curriculum. Yeah, but mostly qualitative manner. Yeah. Those of you who have were introduced the reversible reaction in secondary school, right, you will definitely have heard of the Haber process, which is a very, very important process because it's being used to make ammonia. Yeah, so you have understand a little bit about the Haber process, the condition, the high pressure, relatively high temperature, but not as high a temperature, okay, as we would like. And then of course, the contact process. The contact process is also important because it's used to make sulfur trioxide. Of course, sulfur trioxide is an important ingredient in the making of sulfuric acid. And of course, the production of esters, okay, is actually in equilibrium as well. Yeah, so if you put carboxylic acid and alcohol together in a vessel, you just put it away for a long period of time, then after some time, or maybe after a week, you're going to end up with some ester being formed, but the ester will not be produced exclusively. Yeah, so there will still be some acid and alcohols remaining. Okay, so that's something that you probably want to be aware of. Okay, so for system in equilibrium, the reactant amount doesn't go to zero. Okay, the amounts can be in terms of concentration, can be in terms of partial pressure, etc. Okay, so you reach a plateau where this plateau is what we call the equilibrium amount or equilibrium concentration. And then, of course, the product will reach a certain amount as well. Okay, so we call that equilibrium amount of product, equilibrium concentration of products as well. Okay, so you probably want to be aware that there will be a point in time where equilibrium is established, but whether you are able to measure it, well, that depends on whether the system is easy or difficult to measure. Okay, but of course scientists have a way to measure it, and I think back in 2015 or 2014, yeah, one of the planning question was actually on equilibrium. So when the day comes, then we'll let you try one of those questions. Okay, so the equilibrium which we experience in chemistry, we call it dynamic equilibrium. Why is it? Why is the term dynamic important here? Okay, it is dynamic because when equilibrium is being established, the reactants are still reacting with each other, and the product is still being decomposed back to the reactant. That is something that I hope it doesn't come as a surprise. So both the forward and backward reaction, right, will happen, and the rates of them happening is the same. Okay, so in short, we say that the they occur at the same rates, okay, as the forward and the reverse reaction. Okay, so the forward reaction continues at the same rate as the reverse reaction. Okay, so that is when equilibrium is being established, and that is how you are able to maintain a certain equilibrium amount of your reactant and products. Okay, so are we aware of the idea of a static equilibrium? Yes, we are aware of it. That's something that you probably have played before in your childhood. It's known as a seesaw. So when the two persons sit at a certain distance away from the fulcrum, the seesaw seems to remain horizontal. It's not moving up or down. So this is known as a static equilibrium. Okay, however, right, if you want to imagine what a dynamic equilibrium is, okay, but don't try this, okay, don't try this. Just imagine that an escalator is coming down at a certain velocity, and then you are moving up at the same velocity. So from someone at a certain distance, the person will be, when the person is looking at you, you will appear as though you are not moving. Yeah, so that is known as a dynamic equilibrium. Okay, so you notice escalator going down at the same velocity as you walking or running up the escalator. So I hope that kind of like this is kind of like an analogy to what you would expect to take place in what we call a dynamic equilibrium. Okay, so a dynamic equilibrium for a chemical reaction is when the reactants react to produce the products, okay, at the same rate as the product being decomposed to give you back the reactants. Right, so we're going to move on to the next portion. Nitro, or rather dinitrogen tetroxide being decomposed to give you NO2. This is one of the most well-studied reaction. Whether is it we are talking about chemical kinetics or we are talking about chemical equilibrium. Yeah. So and the reason why is it so well studied in the past is because number one, N2O4 is colorless, then NO2 is brown, so it's very easy to actually detect the amount of NO2 present in the system. Okay, so we are just using this as an example. So if you have a certain amount of NO2 in the system, okay, oh sorry, in this case N2O4 in the system, and then N2O4 starts to decompose, and then you realize that the NO2 will be formed, and then after a while it will reach a certain concentration, which is about 1.6, and then the NO2 will drop to about 0.2. Yeah, from 1.00 to 0.2, and then NO2 will increase from 0 to 1.6. So from here you realize that N2O4, right, the amount that decreased is by 0.80 in terms of number of moles. But because the mole ratio for N2O4 to NO2 is 1:2, so therefore if N2O4 decreases by 0.80, NO2 must increase by 1.60, and this is reflected by the graph, which you can see from here. Yeah, so that is why the amount NO2 went up not by 0.8, but it's by 1.6. Okay, so this is the point in time when equilibrium is being established, so we call it T1, or the time when equilibrium is being established. Okay, then okay, so this kind of graph is what we call a concentration against time graph. If you look at another kind of graph known as the reaction rates against time graph, you'll notice that the rate of the forward reactions, okay, it will slowly decrease from a certain value, from an optimal value, and then the rate of the reverse reaction will increase very slowly as well, but it will reach an optimal value, but eventually both of them will reach the same value over here. Yeah, so this is what we meant by the rate of forward reaction equals to the rate of the backward reaction, or the reverse reactions. Okay, yep, I think I've explained most of the things here, so I think we can just skip this. Yeah, but of course, do take note that it is almost impossible for you to get, for N2O4 to be completely decomposed to NO2. Some of you might be wondering why is that the case. Okay, but in all honesty, to be able to explain this well, you need to understand more thermodynamics. Yeah, which we'll see whether we have time in class for some of these activities, or we can go a little bit more into details. Yeah, but at this stage, I don't think I would like to address why some system the reaction doesn't go to completion, but some goes to completion. Yeah, it has a lot got to do with the absolute Gibbs free energy content of the product and reactant, and how they are being balanced when the product is formed from the reactant or the other way around. Yeah. So if you try to imagine, the equilibrium amount is really when the combination of a suitable combination of the product and reactant having the minimum Gibbs free energy. Yeah. So I'm not going to go into details, but just have a picture like that. So that is probably at a position where they are already the most stable in terms of Gibbs free energy as compared to the pure reactant and the pure product. So that is why equilibrium exists for these systems. Okay, yeah. Okay, so for the next thing, we're going to look at the thermal decomposition of calcium carbonate. Yeah, so again, we probably want to be aware that we can only achieve equilibrium for this particular reaction when we do it in a closed system. Yeah, because for an open system, right, so open container, right, you'll notice that whatever CO2 that has been produced will actually escape. Yeah, so the escape of CO2, right, if you go a little bit by logic, it's actually going to continuously cause the equilibrium amount of CO2 to so-called drop. Yeah, so later on you're going to learn something called the Chatelier principle, but the amount of CO2 that drops over time will actually force calcium carbonate to decompose even more. So we say that the production of CO2, and when you allow it to escape, it will cause the position of equilibrium to lie to the right, and then it will kind of like drive the reaction to completion. Yeah, so these are the language of chemistry that we use. Okay, yeah, so that's in an open system, but in a closed system, that's fine. Yeah, that's fine, because the CO2 hovers around this area. Yeah, and then potentially the CO2 that hovers around can or potentially able to react with calcium oxide and maybe forms back calcium carbonate, although we will try to imagine how that's going to occur. Yeah, but remember, in a closed system, the pressure is really high. Yeah, so at very high pressure, the CO2 probably can do some wonders here, which is beyond our imagination. Okay, yeah. So maybe also let me stress to students that equilibrium can be established or can be achieved in either direction. Because some students think that when we want to establish equilibrium, we must start from the reactants. But are you actually aware that whether you call something the reactant or the product is a matter of perspective? Yeah. So for example, for this particular system, right, you can call hydrogen, okay, and nitrogen the reactant, okay, and ammonia the product, okay. But for this particular system, ammonia is the reactant. You get what do you get what I'm trying to say? Yeah, ammonia is the reactant. Yeah, I mean you can say, oh, I introduced the product first and then format the reactant, but then whether you call something reactant or product is really a matter of perspective. Yeah, so don't be too hard on yourself on whether something is reactant or product. I think most importantly, please define the way you write by drafting out the correct equilibrium reaction. Okay, equation. I mean equations. Okay, so write out the equations and have a good habit of writing out the equilibrium chemical equation whenever you try to explain things. Because if you don't, okay, and I'm being quite serious here. I mean, if you don't do that, then you will notice that many a times whatever you have written in your explanation, okay, it doesn't quite make sense if you don't define what you write with an equation, with a chemical equation. Okay, of course it is possible if your language skill is strong, so then it will be very clear what you're trying to imply to us. But if your language skill is not strong, then I think it is better for you to write out a chemical equation, and then when you try to explain certain things, use that chemical equation as a basis for you to draft your explanation. I think that will help a lot. Okay, so now we have an exercise 2.1. Go something like, okay, I have some NO2 in a closed vessel, and then ask you to sketch a graph to show how the pressure. Okay, so remember earlier on we said that we talked about concentration. Okay, then now we are talking about pressure. Okay, for some of you wondering how come we can just swap the thing around, right? Well, I mean, if you recall the ideal gas equation, which is PV equals to nRT, okay, and then if you swap the concentration term, I mean, if you just swap, I just shift V over to the other side, I'm going to end up with P is equals to NV over RT, and then N over V happens to be the concentration term RT. So the pressure is actually directly proportional to concentration. Yeah. So using concentration for gaseous, sorry, using pressure for gaseous reactor, right, is actually a good proxy. Yeah, if you ask me about it. Yeah. Okay. So how should we draw the graph? Well, I mean, first of all, we need to define what we have here. So we have NO2. Okay, so NO2. Okay, so NO2 should start from a maximum amount. Okay, so we can make a decision. So maybe we'll start off from a certain amount here. Okay, and then when it decomposes, let's say it drops by a bit, and then equilibrium is being established, maybe somewhere in the middle. Okay, I'm going to draw this like this. Okay, so let's say equilibrium is being established over here. Okay, sorry, it's difficult to draw a nice straight line. Yep. Okay, so this is T. So the time T is where equilibrium is being established. Okay, but most importantly, we need to include some additional details. Why are the additional details important? Because remember that the stoichiometric ratio is 2:1. So we need to show on the graph the relative drop in the amount. Okay, so from here to here, I will expect a drop of, let's say, 2 units, 2A units, for example, 2A units. Okay, and then what about the amount of oxygen and NO? Well, the amount of NO should also increase by 2A units. Okay, however, whether it goes higher or lower, it really depends. But from the way I sketch my graph, okay, it seems that the 2A amount will reach probably somewhere here. Okay, so that's 2A amount. So let me, okay, maybe I should draw the oxygen one in first as well. So that's like this. Okay, so we have to label our graph. Remember to label your graph. Okay, if you heard your tutors talk about it in the blogs, then yeah, you should be labeling your graph very clearly as well. So this is O2, NO, and then NO2. Okay, and then we draw the dotted line, and then this is actually 2A, and then of course from here to here this is A. Okay, so that's about it. Yeah, so remember this. I think this applies to all kinds of assessment question or whatever things you're trying to present to people. Whatever you're doing, especially when you're drawing a graph, please label individual graphs. Please indicate what you are trying to show the audience. Yeah, so you just imagine that if you are being presented with this particular piece of information, are you able to understand what exactly is going on? Okay, yep. Okay, next we're going to move on to equilibrium constant. So finally, okay, we are going to introduce a little bit of the mathematics here, but not going into huge details because I think the later chapter will talk about it. Okay, so for equilibrium constant, okay, so first let us look at equilibrium law. Okay, and of course based on equilibrium law, this is how we are going to write out our equilibrium constant eventually. Okay, so for example, if we have a reversible reaction, okay, having reactant A and B and product C and D, assuming that the concentration is written, of course, in the square bracket way, then the equilibrium constant in terms of concentration, sometimes we write Kc. Okay, we still write Kc with a subscript C, just to indicate that it's actually equilibrium constant in concentration. So the Kc is actually equals to the concentration of the products, okay, multiply with one another, raised to the respective power. So in this case, the respective power is actually the stoichiometric coefficient. So in this case, it's C and D. Okay, divide by the concentration of A and then B raised to their appropriate power. In this case, is A and B. Okay, if you recall from kinetics, this is a little bit different. Remember that in kinetics, the order of the reaction is not the stoichiometric coefficient, or it could be, but most of the time it is not. Okay, unless those are elementary steps. Yeah, the reason being for kinetics, the order of reaction must be experimentally determined. But for equilibrium constant is different. Okay, so for equilibrium constant, the power of the concentration term, right, okay, is actually the stoichiometric coefficient. So it is defined by the equilibrium equation you're writing. So be very clear about this. Okay, so therefore it really means that if I write my Haber process as 2NH3 decomposed to give me N2 plus 3H2, the value of the equilibrium constant will be different when I divide everything by 2. Please take note of this. Okay, you might want to prove to yourself why is that the case. Yeah, so this is very important. So I need you to take note of it. All right. Okay, so with the same idea, we can also write an equilibrium expression in terms of partial pressure. So instead of Kc, we'll write it as Kp. Yeah, so in this case, let's say A, B, C, and D are gaseous reactants. So in that case, we will have the partial pressure of C multiplied by the partial pressure of D being raised to their appropriate power, and then the partial pressure of A, partial pressure of B being raised to their appropriate power. But you have to be aware that this only works for gaseous reactants and products. So if the reactants and product are not gaseous, then there's no point in defining a Kp. Okay, so kindly be aware of that. And then is there a relationship between Kc and Kp? Yes, there is. If you want to work out mathematically, you could do that, but it's not the most important thing for our discussion. So I will just skip this. If you're interested, you can read the mathematics. But if you recall what I told you earlier on regarding using the ideal gas equation, then I think deriving the relationship should be a piece of cake. Okay. Yep. Okay. So now we have exercise 3.1. Okay, so for this particular exercise, you're supposed to write down the equilibrium expression for both Kc and Kp, and then state the units. So for gas, you need to assume that the pressure is measured in Pascal. Okay, so yeah, so we'll do the same thing as what we did earlier on. Okay, so for the Haber process, so in this case, Kc is actually equals to the equilibrium concentration of the product. You notice I emphasize on equilibrium concentration and not simply just concentration, because many a times the students will feel that or will mistook all this for the initial concentration. Yeah, these are equilibrium concentration. Okay, so and then divide by the product, the reactant. So that's N2 to the power 1, and then H2 to the power 3. Okay, so in terms of units, I don't think I really need to go into huge detail, so I'll just use the example, the Haber process, to explain. So in this case, the numerator unit will be mole to the power of 2, and then dm to the power of 6. This will be divided by mole to the power of 4, dm to the power minus 24. Okay, so in this case, the units will be mole to the power minus 2 and then dm6. Okay, so we'll do the same thing for Kp. So Kp will be equals to the partial pressure of ammonia, okay, raised to the appropriate power, which is 2 here, partial pressure of N2, and then partial pressure of H2 raised to the power 3. And then, of course, units will be simple. That will be Pa to the power minus 2. Okay, yeah, so for the reversed, yeah, so the reverse will be the reverse. Okay, so in this case, the products will be N2 and then H2 to the power 3, and then ammonia to the power 2. Okay, so in this case, the units will be mole squared dm minus 6. Okay, so in terms of Kp, it will be the reverse as well, Pn2 pH2 cube, and then P ammonia squared. So units will be Pa. Okay, yep. And for the one for part 3, same thing. Kc is equals to concentration of NO2, and then concentration of N2O4 half. Okay, then the units will be mole half dm minus 3 over 2. And then for Kp will be the partial pressure NO2 divided by the partial pressure N2O4 to power to power half. Okay, and then units will be Pascal half. Okay, now I want all of you to pay attention to this. Okay, if I were to indicate this as Kc and Kp for 1, and then for 2 as Kc prime, and then the other one as Kp prime, you notice there is actually a relationship between Kc and Kc prime. Okay, the relationship is actually reciprocal. So Kc is actually equals to 1 over Kc prime. Similarly, Kp is equals to 1 over Kp prime. You notice about that. Okay, so that's something interesting which you might want to take note of in case, you know, when you are looking at interesting assessment questions, or questions slightly beyond the needs of the curriculum, which requires you to use data from the sources. I think that will help a lot. in crafting out an answers. Okay, so we'll move on to 3.2. Okay, so for 3.2, right, what about the equilibrium constant involving, like, let's say I have pure liquid and solids? Because so far we're talking about gases in the vessel, as well as reactant in a solution. Okay, so for A, right, you notice that what we have here is you have solid and solids. Okay, and then for B is not so inspiring because everything is liquid, so that's fine. And then for C you have a liquid for water, so the rest are all aqueous. Okay, so A is known as heterogeneous equilibrium because the system, okay, or equilibrium being established between the product and the reactant, right, involved are in different phases. Okay, for B is homogeneous. It's homogeneous because everything is liquid. For C is also considered homogeneous because the solvent in this case is part of the equilibrium in that sense, but not all are involved, of course. So a little bit of it is involved. So we consider them as homogeneous because there is no clear phase boundary between the reactants and the products. Yeah, so that's something that you might want to pay attention to. So how do we consider something as different phases? So there must be a clear phase boundary. Okay, so if you apply the equilibrium law, okay, at least to part A, okay, so I think it's typed out here for you. So you write them out as CaO, CO2, and then CaCO3, right? If you rearrange them, you'll notice that your equilibrium constant essentially is just equals to concentration of CO2. Yeah, because the concentration of solids are actually a constant. Yeah, because solids have fixed density. Yeah, so whether you have a bigger piece of solid or a smaller piece of solid, the concentration or the density is fixed. Yeah, so usually they will be subsumed into the equilibrium constant. Yeah, so we just call them a K in that sense. Okay, so in this case, Kc is just concentration of CO2. And of course, Kp, which is only dependent on gaseous reactants, yeah, it's just the partial pressure of CO2. Okay, yeah, so something that you need to take note of is that if you are looking at heterogeneous equilibrium, okay, in most cases we'll omit the concentration of pure liquids and solids because they are constant. Okay, and then this portion explains why they are a constant, which I have kind of like illustrate to you earlier on. Okay, how do we connect? How can we connect between equilibrium and kinetics? Okay, so a little bit of background. If you have a reversible reaction, we have the backward rate constant. Maybe we can denote as Kf, and the forward rate constant as Kb, and then the backward rate constant as forward rate constant as Kf. Okay, so assuming that this is a single step reaction, so yeah, so if the reaction will proceed in a single step, so the rate of forward reaction will be Kf. Remember, single step means elementary. So this step alone is the elementary step. And because it's the elementary step, we can actually use the stoichiometric coefficient as our order. Yeah, so if you're a little bit confused, you can go back and revise the kinetics notes towards the last portion. Okay, so we can write this out, and then the backward we can also write this out as well. And then because the rate of the forward reaction is equals to the rate of the backward reaction, we can combine the two here. Yep, and then we shift them around, you'll actually end up with this particular expression, and then you'll notice that this is actually the equilibrium expression. So this is actually the Kc. Yeah, so from here we can establish the relationship between Kc and the forward come backward rate constant. So actually it's actually equals to the ratio between the forward rate constant and the backward rate constant. So you notice that even when I write it out freehand, it's a little bit difficult. Yeah, so for equilibrium constant is usually the big K. okay, or the capital K, or the one with the cap. Okay, rate constant is usually the small k. Okay, so when you write them out, make sure that they are being written out clearly. Okay, however, the expression is only true for a single step reaction. Okay, so I mean, this is just kind of like a proxy for you to know that, you know, like the rates of I mean, the equivalent constant can actually be used as a sort of indirect measure of the ratio of the forward and backward rate constants. Okay, but many reactions do not really follow this, but I think this is just something which we just want to showcase to you so that you have a slightly deeper understanding of the relationship between the two. Okay, so we'll move on to the next part on the position of equilibrium and equilibrium constant. Yeah, you'll notice that this particular term is very important and it shouldn't be used loosely. Okay, when you are referring to position of equilibrium, or POE for short, um, you should use the term position of equilibrium, or you can say position, or you can say equilibrium position. You shouldn't be saying equilibrium shift to the left or right. Yeah, because it doesn't make sense. The position of equilibrium, right, indicates whether um, the the amount of product is more than the reactant. We call it product heavy, or the amount of reactant is more than the product. We call it reactant heavy. So that's the position, whether it lies more to the product side or reactant side. Yeah, but regardless, the whole system is in equilibrium. So equilibrium explain or denote the state where the system is in. Yeah. So when you say equilibrium shifts, so equilibrium don't shift because the system is already in equilibrium. It is the position of equilibrium that actually shifts or lies to the left or right. Okay, yep. So I think it's kind of like explained either here or the later part. Yeah, if I have a small k, knowing that equilibrium constant is being calculated based on the ratio of the product and reactants. If the k is small, it means that the position of equilibrium actually lies to the left, which means it's reactant heavy, or you can say that the amount being converted to the product is little or small. Okay, a big K usually means that it is product driven, or the extent of conversion is huge, position of equilibrium lies to the right. Okay, yep. So I think we have some magnitude here for you to take a look. So if you have a very huge equilibrium constant, that essentially means that the reaction goes to completion. Okay, yeah. But remember that equilibrium constant, right, they being thermodynamic variable, right, do not provide you with information on whether the reaction is fast or slow. Okay, yeah. So some of the reaction can be really slow, okay, but the amount of product is huge. So huge equilibrium constant value. Yeah, but it doesn't mean that the reaction will just happen instantaneously. So it doesn't work that way. Okay, so you might want to pay attention to this. Okay, I think this will also be covered later on, but you might want to take note that the position of equilibrium can actually shift to the product or reactant side depending on a few factors. So that's something you learn under the Chatelier's principle. Okay, but the value of K, which is the equilibrium constant, it is only temperature dependent. Yeah, only temperature can cause the value of K to increase or decrease depending on the situation. Yeah, even a catalyst will not, okay, I repeat, even a catalyst will not change the value of K. The presence of a catalyst, right, simply allows K to be established more quickly. Okay, so the catalyst don't cause K to suddenly blow up in value. No, it doesn't happen that way. So that's something that you might want to be aware of instead of thinking that, you know, like a catalyst is something that you can solve all the problem. No, it doesn't happen that way. Yeah. So that's why chemistry problems sometimes it's difficult to solve, because when you solve one, you create another new problem. Okay, yeah. Okay, we'll move on to the fifth topic, which is on position equilibrium and Le Chatelier's principle. Okay, you might have, I mean, some of you might have learned this in secondary school, especially Le Chatelier's principle, because you learn about the qualitative aspect. Even if you don't learn about it in secondary school, something called Le Chatelier's principle, but you would have used it in your qualitative explanation. Okay, but maybe let me reiterate that Le Chatelier's principle is not like an end-all solution. It is something that was developed and people observe that it helps to explain things. Yeah, but it shouldn't be used blindly. Okay, so let me just emphasize, it shouldn't be used blindly. Uh, I'm not sure whether we will encounter examples like that, but if we do, then I will highlight that to you. Yeah, but if not, in the course of studies for A-level chemistry, you will encounter a situation when if you blindly use Le Chatelier's principle, you realize it doesn't make sense. Okay, yeah. So you need to know. So this is like a recall kind of setting. So you need to know how to state the Le Chatelier's principle. Okay, so basically it states that if the conditions of a system equilibrium is changed, so meaning that if you apply or if you subject the system at equilibrium to some stress, okay, then the position of equilibrium will shift in a direction, okay, so as to reduce the stress or mitigate the stress. Okay, remember, it does not remove the stress, it reduces the stress or the change. So remember this. So don't use the wrong term if you are ever asked this in assessment. Yeah. Okay, so in many cases, students, when they write fast, they tend to say it removed that change. It doesn't remove the change. Because if you remove the change, then you might as well not have you might as well not study equilibrium because you realize that the equilibrium constant will not remain a constant value. Okay, so let us see from here. Okay, first, what if there's a change in concentration? Okay, so in this case, what happens is that we have a system, an initial system at equilibrium. Okay, so we have hydrogen here, 3 mole per m cube. We have ammonia, so we have N2. Okay, so what happens here is that uh, at a certain time t1, I introduced N2 into the system. So N2 is introduced at T1. Okay, please take note of the shape of the graph because it's very important. You'll notice that for nitrogen, right, it shot up instantaneously. Okay, why is that the case? Okay, because when you introduce nitrogen, you introduce them in bulk at one time. Just push the nitrogen in. So almost instantaneously it should shoot up. But the rest needs time to establish or re-establish the equilibrium. Okay, so in the case of hydrogen, okay, it needs to react away some of the nitrogen being added. So it takes time for it to react. So it goes down slowly until equilibrium is re-established. Then the ammonia will also form kind of slowly. So it goes out like this. Yeah, but the amount of N2 that is introduced, the amount will shoot up because they are being introduced all at once. Yeah, so if you are ever asked to sketch a graph, I think these are some of the details which you need to look at. Yeah, so again, the introduction of nitrogen is considered a stress to the system or a change. Okay, so when I introduce nitrogen, it's like the equilibrium, the system is no longer equilibrium. Okay, yeah. So in order for me to re-establish the equilibrium, I need to reduce that change. So in order to reduce that change, the hydrogen present must react some of the nitrogen being added. So in that case, I will form more ammonia. So that explains why the amount of hydrogen drops and the amount of ammonia increases. Yeah, so we need to understand the chemistry behind it, not just blindly memorizing it. Okay, and of course, because some of the hydrogen has been reacted away, it will drop. Okay, so I hope this kind of like, makes sense to you. So it's important for you to understand some of the ideas behind why they are being written in a certain way. Okay, yeah. And then yeah, so these are some of the key points to take note. But when we try to try to do a calculation, you realize that the new equilibrium constant is actually still the same. Okay, so I shouldn't use the word new equilibrium constant. I should be saying that when the equilibrium has been re-established, the equilibrium constant remains the same. So this is very important, very valuable. So I hope you understand this very well. Okay, and then so for a gaseous system, like the change in partial pressure will also affect. So if you add more nitrogen, the partial pressure N2 obviously will shoot up, and then the equilibrium will be re-established. Okay. However, let's say we have such heterogeneous equilibrium. When I add more calcium oxide, calcium carbonate, it doesn't affect the position of equilibrium. Yeah, because the concentration of the solids are the same. Yeah, just having a bigger piece or a smaller piece. Yeah, so the amount of CO2 above it, hovering above it, will still remain the same. Okay, so that's something that you need to take note of. Okay, so now let's take a look at exercise 5.1. Okay, so for exercise 5.1, the system in equilibrium, you have pale yellow iron 3 with thiocyanate, which is colorless, and then after that you form the blood red complex. Okay, so this is known as a complex. Okay, and then you are asked to state and explain the observation when sodium cyanide is added to the above equilibrium mixture. Yeah, so when I actually add more cyanide in, yeah, I am creating, or a stress is being made to the system in equilibrium. So the system need to re-establish the equilibrium. How does it re-establish the equilibrium? Okay, the position of equilibrium will shift to the right. Why is that the case? Because in this case, when I add sodium thiocyanate in, the amount of thiocyanate in the system actually increases, right? So you can say the concentration increases. Okay, so because the concentration increases, right, and this is the stress being introduced to the system, or the change being introduced to the system. Yeah, in order to re-establish the equilibrium, I have to reduce that stress or change. So therefore, I have to react some of the thiocyanate away. So in order to react them away, iron 3 has to come in to react with it. So when iron 3 comes in, I will form more blood red complex. So the position of equilibrium will shift to the right. Okay, then I will be able to observe that the blood red complex, more of it is being formed. And then is this being reflected by my observation in the test tube? Yes, you realize that the blood red complex color actually deepens, or it becomes darker red, something like that. Okay, something along those lines. Yeah, yeah. So you notice about the thought process I bring you through when I explain how you should be explaining when you introduce a stress, whether is it a reactant or product into the system at equilibrium. Yeah, so that is very important when you try to explain things in your theory. Okay, okay. Next, for exercise 5.2, right? We have this hemoglobin. So you were told that hemoglobin is a protein found in red blood cells. So then they try to explain to you. Those of you who are bio students, I think it's familiar to you. But basically, each heme, okay, or rather each hemoglobin has 4 heme group. So this huge piece is actually the heme group. Yep, and then they actually coordinate to the iron 2 via the nitrogen. Okay, and then the oxygen is able to interact with the iron 2 via a weak covalent bond. Yeah, so this is actually reversible binding, and that is how oxygen is being introduced to different parts of the body. Okay, yeah. Anyway, we're not going to the bio aspect, but we are trying to understand the equilibrium aspect. Okay, so when oxygen comes in, it will establish an equilibrium to form oxyhemoglobin, which is this, and then more of it will come in, and then after that I will have 2, 3, and 4 lah. Yeah, because in the preamble you were told that the hemoglobin can bind up to 4 oxygen, and because each hemoglobin consists of 4 heme group and each heme group consists of 1 iron 2 each, so and each iron 2 can hold only 1 oxygen, so 4 heme group means it can hold up to 4 oxygen. Yeah, so that's what it means. Yeah. Okay, so with reference to the above series of equilibrium, comment on the position of equilibrium in oxygen-starved muscle when the partial pressure of oxygen is low. Okay, so what's going to happen when the partial pressure of oxygen is low? So we need to kind of like understand this lah. Okay, so when the partial pressure of oxygen is low, the oxyhemoglobin will actually release the oxygen to the oxygen-starved muscles because it needs oxygen, and for that to happen, it has to shift its position of equilibrium to the left. Whether we are talking about the one with 4 oxygen or 3 oxygen or 2 oxygen or 1 oxygen, it doesn't matter because it has to shift to the left. So when it shifts to the left, oxygen is being released to the muscle, and then after it's being released, okay, it will continue, or rather the position of equilibrium will continue to shift to the left. Yeah, because removing oxygen, it serves as, you know, some form of disturbance to the equilibrium. So removing oxygen will actually cause the oxyhemoglobin to actually release the oxygen on its own. Okay, so do not be confused by this uh, because some students think what exactly is this. Okay, so this means that oxygen is actually floating near the near the hemoglobin with 3 oxygen, but not bonded to the iron yet. Yeah, but this is all 4 oxygen bonded to the iron 2. Yeah, okay, yeah, so that's what you need to be aware of. So in this case, the POE shifts left. And then, of course, where the partial pressure of oxygen is high, same thing, POE shifts right. Okay, to form oxyhemoglobin. So I don't think I need to repeat the explanation for A2 because it's basically the reverse of A1. Okay, so how do people at high altitude, low partial pressure oxygen adapt? Okay, well, I mean, if the person lives in high altitude for a long period of time, I mean, if you believe in evolution, so the genes will actually maybe cause the body to react in such a way that at any one point in time they will have more hemoglobin molecules than us. So because they have more hemoglobin molecules than us, it will actually cause the position of equilibrium to shift to the right to produce the oxyhemoglobin. Yeah, so that their body can function as usual. Yeah, so that's an idea that you might want to take note of. If you are, if you're interested, you can read about it. If you might have heard of high altitude sickness. Yeah, it's all related to the partial pressure oxygen being low, and then we get sick. I mean, we are all like living below 2,000 feet above sea level, so we're not used to having low oxygen content in the atmosphere, and then our body hemoglobin cannot react to that. Of course, if you live there maybe long enough, over at least one generation, then things might change. Okay, but as of now, I think we might need medication to help us adapt. Okay, yep. Okay, I'm going to move on to the next example, which is on the effect of change in total pressure. Okay, so yeah, so for gaseous component, if you have a system at equilibrium, so again, we're looking at Haber process again. So what is the effect of decreasing the volume? Okay, yeah. So again, when you decrease the volume, you know that because volume has an inverse relationship with pressure, so the pressure will actually go up. And then when the pressure goes up, um, the system need to react to this sudden increase in pressure. Okay, so I need to reduce the total number of moles of gaseous molecules. So in that case, in order to reduce it but maintaining the same total pre-equilibrium, similar to pre-equilibrium, I need to shift in a certain direction. Yeah. So in our case here for the Haber process, I have 4 moles of reactants on the left and 2 moles of products on the right. So if I were to decrease the volume of the container, the increase in partial pressure, or rather the total pressure will be felt definitely whether you are looking at reactants or products. Okay, but the increase will actually be felt more, okay, by the reactant side, because the reactant side actually to some extent yes a greater number of moles of gaseous molecules and compared to the product side. But in order for me to re-establish the equilibrium, okay, I need to shift the position, or the position equilibrium needs to shift to the right, okay, in order to mitigate, yeah, the decrease in volume, meaning the increase in overall pressure, yeah, because I need to achieve the middle ground. Yeah, I can't shift left. If I shift left, I'm going further and further away. The overall pressure shoots up. Yeah, so I have to shift right. Yeah, so this might be a little bit difficult to understand. I think it takes a bit of time for you to think about it, but yeah, please give yourself that time to think through, because it's important for you to be able to formulate your argument well. Okay, yeah, so I think whatever I've explained is actually kind of like established here, but it's in a pictorial form. So maybe we try to discuss a little bit using this particular diagram. Okay, yeah. So so again we have hydrogen, we have ammonia, we have nitrogen in the original equilibrium. Okay, so what happens when we actually decrease the volume? Okay, so when this is a little bit different from the earlier example, so please take note of the difference. In the earlier examples, right, we artificially introduce one of the reactants, in that case is nitrogen, so that the concentration shoots up instantaneously because they're all being introduced at one time. Okay, either even if you look at partial pressure, it will shoot up as well. Okay, but in our case here, when we decrease the volume, okay, the partial pressure, or you want to look at it, the concentration of all the reactants and products, okay, will shoot up instantaneously at the time t1. Okay, why is that the case? Well, I mean, they are all experiencing the same container, so definitely whether they like it or not, the drop in volume will affect all at the same time. Okay, but you need to be aware of this. The increase in concentration, okay, it's stoichiometric ratio dependent. Okay, so if you look at your Haber process, the ratio is actually 1, 3, 2. Okay, so the concentration will definitely drop by the same unit, so it has to be reflected in your graph. Okay, respectively. Yeah, so please take note of this. Okay, and then you will notice one relatively interesting phenomenon. Sorry, I think I just accidentally, yeah. You will notice one interesting phenomenon. Okay, so when all of them shoots up, right, what happens? Position of equilibrium will shift to the right, agree? So if it shift to the right, then the amount of hydrogen and nitrogen will drop because they react with each other. Okay, and in the process, I will increase the ammonia. So the ammonia will actually increase like this. Oh, sorry, just increase like this. Okay, so it will increase. Yeah. So no need. There isn't a need to memorize any of these graphs. Let me stress in this aspect. Let me stress. No need to memorize. But on the spot, uh, based on your understanding, okay, derive the relationship. It's faster that way. If you memorize, all hell breaks loose because there's just so many combinations. Okay, yeah. So earlier on, I talked about pressure. Okay, I talked about pressure, but it works whether you're talking about pressure or concentration, because the idea is similar. Okay, yeah. Whatever the case is, the value of the equilibrium constant will remain the same. Okay, so that is something that I thought I just want to keep emphasizing. But of course, some of you might be wondering, um, the reaction is producing more product. What if in the course of the reaction, heat is taken or given out? Okay, so and then you'll be thinking, oh, then the solution will, I mean, the reactants will actually be colder or hotter, right? So it will affect Kc. Yeah, so of course, in reality, we can't control the temperature that accurately, but in this case, in such hypothetical scenario, we will assume that the system temperature is being managed. Okay, so I think when we look at academic explanation, we need to be able to fine tune a little bit. I mean, without going to too many changes. Okay, so with that, I hope you can see that we kept emphasizing Kc remains the same, Kc remains the same. Of course, there is an underlying idea that there is a way for us to manage any temperature rise or fall, if any. So at the end of the day, yeah, um, temperature being kept constant or this, then yeah, Kc remains the same as well as Kp. Okay, uh, then in, using this particular with this particular scenario, right, we have H2 and I2 reacting with each other to give you Hi. Notice that the number of moles of gaseous molecules on both sides is the same. It's actually 2. So in this case, the change in pressure will have no effect on the position of equilibrium. Yeah, so that's something interesting you need to take note of. Okay, and for exercise 5.3 is our next exercise. So we have the following system at equilibrium. Again, a little bit boring. Yeah, same old story. N2O4, NO2 colors brown. So if I increase the total pressure, how will it affect the position of equilibrium? Okay, so in this case, how do I actually increase the total pressure? So most likely that's definitely related to changes in the volume. So I decrease the volume. Okay, so if I were to decrease the volume, um, the total pressure will actually goes up. Okay, and then definitely the effect will be felt more by the product as compared to the reactant. Okay, so in this case, the position of equilibrium needs to shift to the left. Okay, needs to shift to the direction where the number of moles of gaseous molecule is lesser than the other side. So in this case, it shift to the left because left hand side 1 mole, right hand side 2 mole. So if it shift to the left, you notice that the brown color's intensity actually decreases. Yeah. Remember this. Many a times students also forget to describe what you observed. They just happily say position of equilibrium, shift left, shift right, explain everything, say that, oh, like you have to be shifted in a direction with a lesser number of moles of gaseous molecules, therefore it shift left, but they forgot that the question has a follow-up. What would you observe? One is colorless, one is brown. If you mix colors and brown together, it's brown. But if I shift more to the left, the number of moles of NO2 drops, so the intensity of brown actually decreases. Okay, so I hope you I mean going through the idea of equilibrium is not the same as teaching you assessment skills, but these are little things that you need to be mindful of. Okay, answer the question in full as simply as possible. Okay, now next, what about the change in temperature? How will temperature affect equilibrium? Okay, so well, truth to be told, it depends on the enthalpy changed. So in this case, whether is it exo or endothermic reaction. So in this case, we're looking at an exothermic reaction. So for the Haber process, heat is being released. Okay, So when heat is being released, you can kind of maybe to make your life a little bit easier, maybe uh, just put whether is it the products, uh, I mean, okay, when the reaction goes from left to right and it produces heat, of course we will write heat on the product side because it is the production of the product that generates the heat, right? Yeah. So in the very loose sense, if you treat heat as some form of a reactant or product, okay, then I think it's easier for you to discuss how to actually explain when we try to talk about changes in temperature. Okay, so in this case we'll use the same examples. What is the effect of decreasing the temperature? Okay, so do you notice that when we decrease the temperature, it is analogous to removing, or rather not exactly removing, but try to decrease the amount of heat present in the system. So the amount of heat actually decrease, right? Yeah. So this is already some form of stress being applied to the system at equilibrium already. Do you notice that? Because I am removing away the heat that is being produced. Yeah, so if I remove the amount of heat being produced, then of course the position of equilibrium wants to shift to the right because I want to release back the amount of heat that's being removed. I mean, it's not a one-to-one exchange, but it will be able, the system equilibrium will be able to sense the change. So it will shift to the right to produce more heat. Okay, but as I said, this amount of heat is not a one-to-one exchange, okay, but rather is an answer to a stress being applied to the system at equilibrium. Okay, but what are we concerned with? We are concerned with the amount of product we want, right? So we want more ammonia. So if the reactants react to produce more heat, producing more heat also means that more product will be produced. And isn't that what we wish to happen? Yeah, so more product produced. Yeah, so in this case, the amount of ammonia goes up, the amount of reactant goes down. Yeah, so this is reflected by the graph here. Okay, so also take note of what happens, how the graph is being sketched. You notice that at this point in time, when the heat is decreased, you notice that the reactants and the products, they re-establish the equilibrium slowly. Like their amounts will not shoot up or down. I hope you can understand this logically. Yeah, because logically, they should take time to react. Now, the reason why this is different from the earlier example, I think I've already explained to you, is that when the volume is changed, at that point in time, all the reactant and product are experiencing that change, and definitely their concentration will change immediately. Okay, when you introduce a reactant in, that reactant's amounts will shoot up instantaneously. So you need to know the difference. Do not just blindly sketch out the graph. Okay, yep. So in this case, the amount of N2 decreases. Okay, the amount of H2 decreases. Why is that the case? Because I need to produce more ammonia to produce the additional heat. Okay, so as to mitigate the decrease in temperature. All right. Okay, so we have kind of explained this a little bit. Okay, however, please take note of this. As we said earlier on, um, equilibrium constants are temperature dependent variable. Yes. So when we when we change temperature, okay, when we change temperature, it will have an effect on the equilibrium constant. Okay, let me repeat. When we change temperature, okay, after the equilibrium has been re-established, it will have a very, very huge effect on the value of the equilibrium constants, unlike the earlier examples. Okay, so in this case, for the exothermic reaction, because the position of equilibrium shift to the right, the value of Kc actually bumps up. Okay, okay, so that's the nature of temperature dependent variable. Yeah, so remember this. In this case, the drop in temperature will increase the Kc and Kp value. Okay, the increase in temperature will be the reversed because the position of equilibrium will shift to the left. Yeah, so it will be reactant heavy, then Kc, Kp will drop. Okay, yep. Okay, over here, there is a little bit of background information for you to maybe understand, like what exactly is happening here. Okay, so I'll just spend a little bit of time explaining this a little bit, but the bulk of it has got to do with the Arrhenius equation. Okay, so perhaps let me explain this using the example earlier on, the the Haber process. Okay, now based on our understanding of Arrhenius equation, okay, and of course based on logic lah, okay, based on logic for rate constant, right? Increase in temperature, rate constant will go up. Okay, because our usual understanding of reaction is that the higher the temperature is, the faster the reaction, the lower temperature is the slower. So yeah, so the rate constant is proportional. There is some relationship with temperature. Okay, so in our case here, for the Haber process, you need to take note of, let me repeat, you need to take note that when we decrease the temperature, both the forward and backward rate constant will decrease in value. Okay, the value will drop definitely. Okay, so please understand that nothing has changed from what you learned earlier on. So both your forward and backward rate constant will decrease. Okay, so the reaction will become slower. Okay, so remember this. Okay, however, right, because the forward reaction is exo, remember this, our Haber process is exothermic, right? Okay, so the backward reaction will have a larger activation barrier. So remember this. When we look at an exothermic reaction, okay, I'm not going to label the x's, so we're going to have something like this, right? So the forward barrier is here, the backward barrier is here. So it will have a larger uh, backward activation barrier. Yeah. So because of that, the decrease in Kb will be greater as compared to the decrease in F, the forward rate constant. Yeah. So on the whole, okay, on the whole, K will still increase. K as an equilibrium constant will still increase. Yeah. Okay, so remember this. And the same explanation works for exothermic processes. Okay, so if you are able to understand this, I think you should be able to tackle all questions on equilibrium, even MCQ, because usually MCQ, student misconception, right, will actually pick the wrong option when we ask them about KF and KB. Okay, yeah, and if you are interested, you can maybe move on to go and study or analyze a little bit more about the Van Hoff equation, but I will not attempt to go into details. Okay, so I will leave you all to read more, and as I mentioned earlier on in thermodynamics all the way all along, thermodynamics and equilibrium are intimately related, although it seems that in H2 Chem they are taught kind of separately. Yeah, but it's important for you to understand that these two concepts are intimately linked. Yeah, and if you go to university to do chemistry, you'll realize that a lot of it, um, uh, you'll be able to see the link between the two, and you'll have a more complete view of it. Yeah, so if you're really interested in understanding more, yeah, please come and have a word with me, and or if you can read more about it through physical chemistry textbooks. Okay. Okay, next we are looking at exercise 5.4 over here, but before that, we need to look at a video. So I have this particular video to show you so that you can have a more interesting understanding on how does temperature affect cobalt complexes. Okay, so I'll go to the video. Okay, so I will just voice over a little bit. So what happens here is that there's this particular cobalt complex which is pink in color. So this particular cobalt complex is actually what was being written on your on the lecture book on exercise 5.4. It's what we call the hexa aqua cobalt 2 complex, which is pink in color. Okay, I know it's written here as cobalt nitrate, but it simply tells you that this is the salt, the cobalt nitrate salt that I dissolved, which I dissolved in water to give me this particular solution. But the nitrate do not play a role in the color in this case. Yeah, it is the aqua complex, which is the hexyl aqua cobalt 2 complex that plays a role in the color. And you're going to learn why is it pink, or rather not why is it pink, but why is it colored when you move on to JC2 under transition metal. Okay, so this is just a bit of background in case you're wondering what to focus on. This is called hot plates. You might have seen them in the lab, maybe. If not, then you will get to use one soon. And then there's a cold water bath here. Okay, and over here we have concentrated hydrochloric acid. So what the demonstrator will do is she will add the concentrated hydrochloric acid into the solution, and then you will notice a change in the color. Okay, why is there a change in color? Because the chloride replaces the water in the complex. So okay, so in the complex, chloride and water are what we call ligands, spelled as Ligand lah. So it's called ligand. Yeah. So the chloride actually displaces the water ligand and form the tetrahedral complex, which was what's being described in exercise 5.4 as COCl4 2 minus. Okay, so let's watch it. In a small beaker, we have a pink solution of cobalt nitrate. First, we're going to add 12 molar HCl dropwise until the solution becomes purple. So you notice that she's adding quite a bit of concentrated HCl, and then the color change gradually. You can see that as the drops are added, you can see a little bit of purple appearing in the beaker. This will take some time, so just a moment. Okay, so I'm going to fast forward. Oh, okay, it's there. As you can see, it took almost 15 milliliters of 12 molar HCl to turn the solution from pink to purple. Okay, so you notice that this color is purple or lilac. It's not really pink or blue as being described in your lecture book, right? Do you notice that? There's a reason for that because both complex coexist. Yeah. So that is why we need to have the hot plate and the ice bath for you to see the difference. Okay. Solution between two. I'm going to fast forward, and then you get to see the ice. Okay, so one in iced, the other one in the hot plate. Now we wait. So they waited for 3 minutes. They took out. The solution on the hot plate is blue. The solution on the hot plate is blue, and you saw that in the color description for the tetrachlorocobalt complex. Okay. The solution in the ice water is pink. It goes back to pink, okay, which indicates the presence of the hexa aqua cobalt 2 complex. Let's compare those solutions to the original purple solution. Yeah, so this is the original purple solution after the addition of concentrated hydrochloric acid. Okay, so you notice that this color, which is kind of like purple, is like a mixture between the two. Okay, so yeah, so what do you notice over here? So I think the first question asks what was the color of the solution at room temperature, which is pink. I think we have done that earlier. I mean, it's like a no-brainer. And then when I heat it up, what's going to happen? So the solution turns from purple to blue, okay, and then after that for the other ice bath, it turns from purple to pink. Okay, so of course now the question is deduce whether the reaction is exothermic or endothermic. Okay, so well, I mean, actually you only need one experiment to help you, but you can use both if you want. Okay, so maybe I'll just use the one that happens first lah. I mean, which is part B. So when I actually heat up the solution, okay, it turns to blue. So that actually tells us that the position of equilibrium shifts to the right when heat is being introduced. Yeah. So what does that imply? So when I introduce heat, what happens to the system? The system experiences stress from the additional heat uh, which I introduced. Yeah. So in order for the equilibrium to be so-called re-established, so-called, I need to reduce the amount of heat that which I introduced at the start. Yeah. So the position of equilibrium will shift in an appropriate direction so as to reduce the heat I introduced. So it prefers to shift to the product side, which is blue. So if you recall what we did earlier on, for it to shift to the right, um, the forward reaction must be endothermic. Yeah, because I cannot shift to a side to generate more heat, right? Because I already produce heat. So therefore, uh, the side with the heat content, with a greater heat content, must be the reactant side. So position equilibrium shift to the right to actually produce more products, and in the process, it mitigates the change by um, reducing some of the heats being introduced. Yeah. So therefore, the forward reaction is endo. Okay. You can also explain it from experiment. I mean from part C. When you put it in an ice bath, it turns back to pink. So what exactly is happening? So when you put it into the ice bath, the ice bath content, the system actually remove the heat. So in order for the system to generate heat, so-called, the system will have to shift the position of equilibrium to the left so as to produce more heat, right? So in this case, how do I know it shift to the left? Because the color is pink. Yeah, I notice it by looking at the color. Yeah. Okay. So yeah. So I hope this particular YouTube video helps you to understand this concept perhaps a little bit more, so that you are in a better position to explain Le Chatelier's principle when you're faced with a change in temperature, a change in partial pressure, concentration, or even the addition or removal of reactants and products. Okay, yeah. Finally, we are at 5.4. So over at 5.4, we're looking at the effects of the presence of a catalyst. I have earlier on kind of like talked about this a little bit already. So the catalyst actually has no effect, okay, on the position of equilibrium. Okay, uh, it merely allows the equilibrium to be established at a faster rate. Okay, so you might want to be clear about this, and it allows the equilibrium to be re-established at a faster rate by providing an alternative pathway for the reactants to react. Okay, so this alternative pathway is being reflected by the dotted line over here. Okay, so I think that's about it for this. So the alternative pathway have a lower activation barrier for both the forward and backward reaction. Okay, so Kc, Kp aren't affected by the presence of catalysts, but they are being brought to the equilibrium at a faster rate. Okay, so that will be the end of the first segment for the video lecture. So the next lecture we will be talking about 6 onwards.